Hello everyone, welcome to our channel Wisdom and Mind. In this video, we will be giving you a code walkthrough of this Monkeypox the classifier model. And in this, we'll be first talking about the data set, how the dataset looks like, how it is, how the images are looking in the data set physically. And then we will give you a code walkthrough of the Monkeypox classifier model. So, before jumping into the notebook and seeing all the steps, I'll quickly show you the data set that is monkeypox lizard, skin lizard data set. So, we are using basically this data set. It is available on Kaggle. There is monkeypox skin lizard data set. And here we have basically two classes, monkeypox versus non-monkeypox. And non-monkeypox class includes chickenpox and measles images, whereas monkeypox consists of only monkeypox images. So it is basically a reclassification problem where we have two classes, monkeypox and others. Now, if we quickly see the description of the data set, so you can see that here it is mentioned that the images are actually web scrapped. So it is not the actual still listen images, but they have taken from different news portals, website, and publicly accessible case reports. Because the skin listen examples or images are not available online, maybe through any research data set or from any other source. So that's why they have used web scraping for extracting the images from different sources and open source portals. And this listen data set is actually focused on distinguishing the monkeypox cases from the similar non-monkeypox cases because we know that monkeypox disease is quite similar to uh, other types of skin disease like chickenpox, measles, smallpox, because their effect or their symptoms are almost same. Only thing is that monkeypox rashes or effect is quite um, severe in comparison to other diseases. So now, if we see the original folder structure, so you can see that there are three folders: original images, augmented images, and fold one. In original images, we have around 228 images. Okay, around 228 images we have, which are the original images, out of which 102 belongs to monkeypox, and remaining 126 belongs to other class. That is non-monkeypox. So you are free to use these set of images, that is original images, and on top of that, you can perform some augmentation based on your requirement. The second folder is augmented images. If you don't want to do augmentations, so you can use this folder because it is already augmented. And they have used different augmentation techniques like rotation, translation, reflection, shear, hue, etc. Apart from that, for doing the augmentation, they have used MATLAB R2020A. Okay. So you can definitely use that uh, because it is properly augmented using proper software MATLAB. And you can see that the class monkeypox and others after augmentation includes 1428 and 1764 images. Okay, so you can use it because now we don't have problem less images. We have already augmented and have a good amount of information. Now there is a third folder that is fold one. And it is one of the three cross validation data set to avoid any type of bias in the training. They have used three cross validation. So in this, basically, you can see that it is also consisting of large number of images like 1428 and 1764. And So in this project, basically, we have used this fold1 folder, and within this folder, we have a couple of other folders. Let me show you in that. So this is fold1. If you click on it, you can see another fold1. When you click on it, there are three fold1 structure. And when we click, there are three other folders: test, train, and validation. Okay. And in every folder, let's say test, we have two folders, Monkeypox and others. And if you click on Monkeypox, they are all the images of Monkeypox in it. So like that, this is the folder structure. So if you understand the dataset structure, then only we can give you a better clarity or understanding to our code for building Monkeypox classifier. So as you have seen the overall structure of this data set, so now we can quickly jump to our Jupyter notebook. So here, let me zoom a bit. So in here, we are actually inputting the necessary file, the necessary libraries, Python libraries. Okay, and we are also mounting our drive because we have loaded the data set on our drive so that we can save all the results, models, everything in our drive for later use. Now the first step is we have to set the path of the directory. After mounting the directory, you can set the path like this: content drive, my drive, and then whatever your dataset name. And within that, you have to give that which um, folder you will be using it. So for train, we have actually renamed the fold1 folder and to Monkeypox dataset. Okay, so don't be confused of that. So you can also rename it, or you can also keep it as fold1. In here we have one folder train, and in here train, or within the train folder we have monkeypox folder. So for getting all the monkeypox images, we are setting mdir directory, whereas for others we are setting odir directory. Then this part basically, if you want to store all the files from that directory, or you want to list all the files basically within this directory, so for that we are creating os.list directory, and we are passing that to name, that is mdir. Okay. Now, uh, as we have set the path, now the part is we have to show the sample images. Okay, so how the images are looked. So this is the monkeypox sample images. You can see that how severe it is. Okay, the rashes are also big, and also it is spread mostly in hands, foot, or mouth, maybe. Okay, mostly it affects hand, foot, and mouth. Whereas other diseases like chickenpox and measles spread over the whole body. So that's the main difference. Now, if you want to see the others images, so others images like this, you can see it is spread whole body. You can see that. Okay. So after reading the sample images, we actually have to load the images. So this is the data preparation step. We'll actually load the image and all the labels. So in here, what we are doing is basically we are creating two lists first, that is data and labels. In data, we'll be storing the processed image, and that too in the array. Whereas in labels, we will be storing all the labels. Okay. So because in the list, we cannot save the image, right? The physical image we cannot list. So we have to convert the image into arrays, and then we have to store it in the form of list. And in the same way, we'll be storing the labels, associated labels, and later on we will combine. Okay. So as you can see, we are iterating over all the M images, which is nothing but all the images in the M directory or the monkeypox directory, whereas O images is the list of the images in the others directory. Now we are iterating one by one for all the directories, and in here we are actually reading the images first using OpenCV library CV2, And in CV2, we are using IM read. And under IM read, you have to mention the whole path of the image for reading it. So what we are doing, we are mentioning M directory, which we have set it initially here. Okay, this is the actual path of the Monkeypox directory, and this is the M images. So we are mentioning M directory plus M. So M is nothing but the each single image within the M images. Okay, so it will read iteratively the images one by one. And while reading one image, it is converting the image into RGB format from readings. And then we are resizing it into a size 224 to 24. After that, we are appending this array image, which is resized image, into a data list. And while appending it, we are also converting it into np.m. Okay. So now we have image in the form of array and associated label we have assigned one. So all the monkeypox images we are assigning the label one, whereas for others we are assigning the label zero. So in the same way we are doing for other images also, and in that way we have after iterating all the images, we will get all the images in the form of arrays in data list, and all the labels, associated labels will be in the labels list. Now we have uh, now after we have just read all the files and stored it in the list. Now we have to convert the labels in the form of arrays, and we are doing it using np.array and passing the list. Similarly, for labels, we are doing np.array and passing the labels. Now the thing is, why we are doing it, because we have to convert whole thing into NumPy array so that we can later uh, just load these arrays, because they are faster in execution, faster to load. So you don't have to do this step every time, because it is a time-taking step. Because if you have more number of users, it will take lots of time. So that's why it is recommended to convert it into arrays and then read it from those saved arrays. So we are basically saving these arrays, that is data and labels, into proper location in our CPU, where we are mentioning the whole part and the variable. So once it is saved, we have to just load it. Okay, so we can load by just mentioning the two parts of the uh, features and labels. Now, you have seen that we have actually read the files sequentially. Okay, so it may happen the uh, multiple images arranged first, and then we have arranged other images. So it has a pattern, right? All the first, let's say 150 images multi-box, and then next 150 images other images. So to remove this sequential arrangement and arrange it in the form of random arrangements, okay, so that the model not get the mistake. So for that we have to basically shuffle. So here we are actually shuffling the index of the data set, and the shuffled index we are adding it in our list, so that the list will be whole list will be shuffled based on that shuffled index. Okay, so now we are putting the number of classes and length of actual data. Okay, so we have total 2052 images, and in these images, this is the whole data set we'll be using it. So we will divide this data set into train and test set, and after building our model, we'll test our model, validate our model on actual validation data. That is, if we go to our data set, that is the monkeypox data set. So here we have train, test, and validate. So we will train our data on train set basically, and also we are testing it within the train set only, and actually validating on val folder where we have both the monkeypox and others images. So we are using this val folder for actually validating, and this validation folder is completely unseen to the model, so because we are using only the train images, so if we validate on this, then we'll get the actual estimate of how the model is actually behaving on unseen images. Well, you can also use test images also, because but in test images we have very few images, around 20 to 25. So, but you can also do second level validation by running your model on this. So after loading the data, we will split our data set into train and test set. So for this, we are using 80% for training and 20% for testing. Next, we have to normalize our image. So for normalization, what we are doing is we are dividing our images by 255. And why we are doing this. So that I have already explained in my previous video. So if you have not seen my previous video, that is COVID chest X-ray detection, COVID detection from chest X-ray, you can just see that. In that, I have mentioned why we are using dividing by 255 and how it will happen. So next, we are using one hot encoding. In here, you can also use you can simply use variables for that, but for simplicity, we have used only one hot encoding as the as actually encoding our categorical variable, that is target variable. So after that, we have to load our model. So for loading, we have to mention certain parameters within that. So mobile net V2 we are using. And here we are mentioning include top is equal to false. Okay, so we'll not be using the top layers. We are using only the uh, actual layers which are helpful in further customization. Okay. Now we are assigning weights is equal to ImageNet. So as we know that all the models like SNet, VGG16, V2 are trained on very large dataset, that is ImageNet dataset, which has hundreds of categories. So we'll be using its main power for basic classification. Okay. So to use their basic capability, their main capability of identifying different classes. So for that, you can use ImageNet weights. Okay. So here we are using ImageNet weights, and further for customization, we are telling that the base layer may be trainable true. So this base layer we will make it trainable. Okay. And after that, in the end, maybe in the fully connected layers, we will be doing something like we are doing average pooling to basically reduce the number of features. Next, we are adding some dense layer. Okay, then we are adding some dropout. So why we are using dropout? So it helps in basically reducing the overfitting of the network, because it occasionally what it does, it uh, cut off some of the neurons while the uh, during the learning process, so that it helps in breaking the symmetry of the neurons, so that there will be no specific patterns in flowing the information. So if we remove the certain symmetry by deactivating certain neurons, so it will do the uh, learning independent of any specific pattern. So this will reduce the overfitting. So that's why we have to use it. And next, we are using again one dense layer with 64 neurons. Next, we are using a last layer, that is actual classification layer. And here we are using softmax function, softmax activation function, and we are setting it as 2 because we have two classes. Now we are combining everything, that is base input and predictions here. And now the one thing is that we have to compile our model next. So for compiling, we have to mention the loss optimizer and the metrics on which we'll be evaluating our model. So loss, we are using binary cross and copy because we have two classes only. Optimizer, we are using Adam because it, most of the time it performs well. And metrics, we are using accuracy. Now, if you see the summary, so very big summary because we are doing mobile. So all its blocks and layers will be shown to you. Okay. So if we go to the just bottom, so here we'll see the information like total parameter, trainable parameters, and non-trainable. So why we have non-trainable parameters? Because we have set certain dropout, which it will be uh, occasionally removing certain parameters from dataset, and also we are setting top as false. So it will not use all the layers present in the mobile. Next, if we see this, so these are some callbacks we'll be using. The checkpoint is that when we should save our model. Okay, so we should save our model. So we have to give the path of the weights or the name to the path of the weights. And then we have to mention which thing we will be monitoring, validation accuracy, validation rules. So here we are actually monitoring validation accuracy. So, and the mode will be max. So maximum validation accuracy it will save in each and every epoch. So in every epoch it will compare what is the validation, maximum validation accuracy it has saved till now, and if the current epoch's validation accuracy is higher, so it will just store that highest validation accuracy. And here also we have mentioned save based only true, so it will only save the best, that is highest validation accuracy based weights. Now the second thing is that more towards make the learning process more correct. So how we are doing it? We are actually reducing the learning rate once we observe that the model is not learning for consecutive two epochs. Maybe you can set it by tweaking this parameter patience. So patience 2 means after two epochs, if the model is not learning, the validation loss is actually not uh, decreasing. That means the model is not learning properly. So in that case, what we'll do, we'll reduce the learning rate by a factor of 0.5. And how much percent it can be reduced? What is the minimum limit? So minimum limit we have to set like min square LR is equal to this. So up to this point, it will be reduced. Before that, after that, it will not reduce. Okay. So here we are wrapping all our callbacks into one list, and now we are fitting it. So we are specifying X train, Y train are both size. So here batch size we are using actually 32, and that we have mentioned in this hyperparameter. Batch size 32, epochs is 50. So if we go here, so you can see that yes, we have set it the size, we have set it the callbacks. Now in validation data, we are setting X test and Y test, and epoch we have 50 and verbose equal to 1. So what verbose 1 does, if you set verbose equal to 1, so it will give some information during the training, all the information like how is the validation accuracy we are saving based on the checkpoint, whether learning rate is reducing in every epoch or not. Okay. So as you can see, the model has done a pretty good job for all the 50 epochs. Okay. So after 50 epochs, we achieved 97.90 accuracy. And if we can see the overall history of the model, so you can see that after around 35 epochs, the model learned pretty well. Its accuracy reached more than 95%. Similar is the case with the validation rules. After 35, 40 epochs, the model stabilizes. Now we are actually loading our model based on the best weight, that is highest validation accuracy rate. So if you see that the model is giving 97.89% validation accuracy on test set, and this test set is nothing but the training, the actual train test set which we have used during the model training. But this test set is not completely unseen, so we cannot rely on this accuracy. So for that, what we are doing, we are loading our validation data set, which we have already converted into NumPy arrays. So same way we are doing it and normalizing it. Now, if we check the model's accuracy on this validation set, which is completely unseen to the model, so you can see it is getting 78.80% accuracy. So if we see the confusion matrix on this validation set, so you can see that it has done pretty good job for monkeypox cases. That is, out of 168 images of monkeypox, it detected 150 correctly. Whereas for others cases, it predicted 181, and around 71 cases it predicted as monkeypox. And that's maybe the reason that some of the cases look exactly similar or somewhat closer to monkeypox or vice versa. So now if we see the classification report, so for zero, that is for others, we have 72% recall rate, detection rate, whereas for monkeypox it is 89%, that is good. So overall, the model has done a pretty good job on this data set, because in this data set we don't have much variations, but we have augmented the images. But sometimes augmentations are also not enough, because in augmentation we cannot get all the variations. But in training or validation set, it may happen that some of the images are totally out of the sample from the training set. So that's why it is giving results like this. So now, if we see the validation, if we see the sample predictions. So you can see here we are actually uh, label it as prediction, and within the bracket we are mentioning the actual label of the image. So you can see that here we have around 3 wrong predictions in the sample prediction, whereas you can see the actual image is monkeypox and predicted others. Why? Because the rashes look quite even, or maybe not that much severe, and that may be the reason that this is the initial stage of monkeypox. So that's why it is not developed properly like usually monkeypox infection looks like, on which the model is trained. So that's why it has predicted as others. Whereas these two cases are actually others, but the model is predicted as monkeypox. Okay. So you can see these images are not that much looking severe, or it is looking more evenly spreaded. But in this case, it is predicted as monkeypox. So the reason may be, as I have told you, that the images are looking quite similar to uh, monkeypox. Images are looking quite similar to other diseases like and vigor, or some of the other images may also look like monkeypox. So that may be the reason that the model is not that much accurate, but it has done a pretty good job. And if we increase the number of images, and if we play with some of the hyperparameters, so the accuracy may also increase maybe by 5 to 10%. And in that case, you can deploy this model on production so that you can check whether the model is doing good job on actual data, actual images. So thanks for watching our video, and stay tuned to our channel so that you will get more interesting videos. And if you have not subscribed our channel, then please do subscribe to the channel so that you will get the notification of our latest interesting video. So thanks guys for watching our video. Have a good day.